Hello, uh, this is a class of deep learning for NLP, and today we are going to study the transformer, which is the most widely used network architecture for modern AI nowadays. Uh, this is this was proposed for natural language processing field at first, but now we use this architecture, transformer architecture, for everyone, almost every AI-related field. This is the general purpose network. Okay, and today we will focus on the multi-head attention and how to process the input and the attention in decoder. So there are many parts, many sub-modules in transformer, but we will only focus on the multi-head attention, positional encoding, and attention in decoder today. Remaining parts will be covered in the next lecture. So far, we have studied in the task dimension, sentiment classification, which can be formulated as text classification, has been covered. Machine reading comprehension or question and answering also have been covered. And machine translation, which was formulated as statistical machine translation for the 10 years ago. And after that, this machine translation is formulated as encoder-decoder architecture. In the formulation side, we covered text classification, token classification, and retrieval, and text generation. Actually, this machine reading comprehension is not directly related to the retrieval, but in the real world, there are lots of documents, and we cannot use our machine reading comprehension model for all those documents. So we have to perform retrieval to narrow down the documents of our interest. And machine translation is basically the text generation, because we have to generate a sentence in another language in machine translation task. In the model side, there are RNNs, which was the dominating model for 10 years ago, or LSTM. And encoder-decoder, encoder-decoder architecture, and attention mechanism, and transformer. Okay. So all these models can be used to serve these tasks. And in the learning side, we only have covered the vanilla training, not pre-training or fine-tuning yet, not in context learning yet. We will see this pre-training and fine-tuning briefly in the next lecture, I think. Now, this is the overview of transformer. The encoder-decoder is very powerful, especially in machine translation. Encoder-decoder, in the last class, we have studied the encoder-decoder architecture with LSTM or RNN. But people realized a few problems with it. This is the encoder, decoder with RNN. Okay. The RNNs are sequential by definition and not parallelizable. We have to wait the previous output to compute the current output. Okay, so that is sequential, and cannot be parallelizable. Hence, this is not GPU friendly. And attention from decoder to encoder is very good. But encoder to encoder attention is also needed for long input. Suppose that we have very long sequences and the conventional RNNs, only the last token no. So if we have very long sequences, there is no way to make the early tokens to influence strongly for the final output, right? So that is the weakness of RNNs. We have already mentioned such weaknesses. So that is why we need encoder side attention. If we can use attention in the encoder side, then we can model the long distance relationship between the tokens in the input sequence. And notice that attention at each time step allows you to only look at one tokens. So ideally, we want to make our attention can see many tokens as possible, right? For example, this is the decoder side. This is the encoder side. And this is the attention. A1, A2, A3, A4. We want to make this A1 to A4 is not sparse. We want to make this attention vector as a dense vector. But in practical, this is very spiky, which means sparse. That means, for example, this is an example. This is one of the example of attention. That means this only using the last token in this case. There is no much usage of the second and third tokens, and there is no usage of the first token in this case. And this is the general case if we use the attention. Still, this is better than RNN because we can use we can model the long distance relationship, right? Even if we our attention only looks at one token at a time. But this is somewhat limitation of the attention. So in 2017, Google researchers were interested in inventing a new type of encoder-decoder that can solve these problems at once. These three problems are solved at once. Parallelizable and encoder side attention and can see multiple tokens at a time. Okay, and this is realized by transformer. The paper named "Attention is all you need." This is a Newrips paper. I think this is weird because this is pure NLP paper, right? If you see this paper, then you realize that there is no other way of no other experiments other than NLP. So I think this can be published in the EMNLP or ACLs, which are the natural language processing conferences, but they choose to publish this paper in the Newrips, which is the top ML conference. And this trend goes on until now. So basically, some technology, some basic or not basic, some fundamental techniques are published in the ML conference, and applications are published in the natural language processing conferences such as EMNLP or ACL. This is very similar in the image domain. The applications, but not every fundamental paper are published in the ML conferences, and it depends on the time because these conferences have deadlines. So if your work was done at May, then it will be published. It is highly likely to be published in the Newrips because the deadline of the Newrips is May. And if your work has finished at November, then your paper will go to the CBPR and so on. Anyway, they decided to publish this paper in the Newrips. So if you want to more fundamental techniques, if you want to make or study more fundamental techniques, then I recommend reading. I recommend to see the Newrips papers or ICMR papers. And this paper is from the Google Brain and Google Research. The important thing is that the motivation of transformer is like this 3 point, not parallelizable, and encoder side attention, and attention only look at So only a single token. So um, this is the overview, the uh, the data pipeline of transformer. So there is no RNS. Instead, they use positional encoding. Why? In RNNs, by definition, we can distinguish the tokens. The position of we can recognize the position of tokens in RNNs without any processing, because the first token goes into the RNN first, and the last token will go into the RNNs in the last. So that is how we can recognize the position of tokens in the sequence, in the sentence. However, in the transformer, there is no way to recognize the position of token in the sequence. So that is why we have to process the input tokens in a specific way to ensure that our model can recognize the position of the tokens. And there is no RNNs, so we can enable GPU parallelization. That is one thing. And use self-attention only, not for encoder. In decoder, there is a cluster attention. We will see what is the self-attention and what is the cluster attention. So don't worry about it for now. And they proposed multi-head attention. This is the addressing the third limitation, number 3. The attention only look at a single token. But if we use the multi-head attention, then this limitation can be reserved. And unidirectional attention for decoding. And all these characteristics enable the model to be scaled up and simplified, which led us to be more freed from model-centric paradigm. So for transformer, it is very easy to scale up the network. Here you can see the n. That means this is the number of layers. This is the layer. This is the layer. That means this one is repeated n times. And also, this one is also repeated n times. Okay. If we increase the number of n, then the network will be bigger. That means the network is scaled up. The other way for scaling up the network is using more number of more number of heads for attention. Okay. Hmm. So, for example, there is 16 heads in multi-head attention. Then, if we want to scale up, then we can use 32 or 64 heads for this model. Then, our network will be larger than before. So, this way is very easy to scale up the network, right? This is impossible in the RNNs or LSTM because if we use more time step, then it might be the gradient vanishing problem will be severe. But in transformer, there is less risk of it. 자, 그래서 트랜스포머 오버뷰를 좀 봤는데요. 트랜스포머는 이제 인코더 디코더 그 지난 시간에 봤던 인코더 디코더를 RNN으로 구현한 것의 약점을 극복하기 위해서 탄생했습니다. 어떤 약점들이 있었느냐 살펴봤더니 세 가지가 있어요. 첫 번째는 패러럴라이저블하지 않다. GPU의 가속이 어렵다라는 거였고요. 두 번째는 인코더 투 인코더 사이드, 인코더 사이드 어텐션이 없다. 그리고 이제 어텐션 했더니 토큰 한 개만 본다. 이 세 가지 약점을 한 번에 해결하기 위해서 2017년에 구글에서 이제 논문 하나 썼습니다. 어텐션 is all you need라는 논문 하나 썼고요. 이게 이제 전설적인 논문이 되었죠. 그래서 꼭 NLPS뿐만 아니라 거의 모든 현대 AI 관련된 곳에서는 이 트랜스포머 구조를 사용하고 있습니다. 그래서 여러분이 꼭 NLP를 할 게 아니더라도 이게 뭔지는 정확하게 알고 있어야 돼요. 거의 CNN급으로 중요해졌습니다. 여러분이 뭘 하든 간에요. 어, 그래서 트랜스포머가 뭐냐? 이렇게 생겼어요. 그 RNN을 전부 다 지웠다. 대신 포지션 인코딩을 추가했다. 왜냐? RNN에서는 그 포지션을 알 수가 있어요. 언제 들어갔냐 보면 되거든요. 성큰이. 근데 이 트랜스포머에서는 그게 안 돼요. 그래서 특별한 처리를 해줘야 되는데 그게 포지셔닝 인코딩이다. 그리고 셀프 어텐션을 쓴다. 인코더에서는. 그리고 디코더에서는 셀프 어텐션과 크로스 어텐션을 씁니다. 그 다음에 멀티헤드 어텐션. 세 번째 리미테이션을 해결하기 위해서 멀티헤드 어텐션이 사용되었고요. 그 다음에 이 모든 캐릭터리스틱이 굉장히 쉽게 스케일업 될 수가 있어요. 그게 이제 트랜스포머의 특장점입니다. Okay? So let's see this figure. The inputs are processed uh, to make embedding. We already know how to make embedding, word embedding, right? And we add the positional encoding to the input embedding. The positional encoding is some kind of noise. But nowadays, we do not use the positional encoding. Anyway, back then, they used positional encoding to process the input embedding. And this goes into the multi-head attention. There are three arrows, right? Three arrows for the multi-head attention. That means there are three input arguments for the attention, multi-head attention. And the output of multi-head attention goes into the add and norm, which is normalization layer. What is add? Add is corresponding to the this arrow and this arrow. So this tensor is added to the output of multi-head attention. That is it. And then normalization. We will see this normalization in the next lecture. And the output of this normalization layer goes into the feed-forward, which is the MLP with red loop. And also, the output of this MLP is added to the output of the input of the MLP, right? So this is basically skip connection. This skip connection comes from the image domain, ResNet. And this skip connection is known to address the problem of gradient vanishing. And the output of this normalization layer is goes into the another multi-head attention, right? So this is repeated n times. And finally, after n repetitions, then this is going to the decoder side multi-head attention here and here. Notice that there are three input arguments, and the two among them, the two input arguments come from the encoder side, and the other input come from the masked multi-head attention. And here is the output, which is a shifted input. The output converted to the output embedding, and also we use positional encoding to process it. And this goes into the multi-head attention. And here is a skip connection. Why masked? That is, the reason is that we want to hide the tokens in the next sequence, next time step. That means the model cannot look forward. Okay. Model cannot look forward by mask. If so, this decoder predict the next token, and if the model can see the next token, then the task is too easy. So we have to hide the future tokens. That is why we use mask here. And then still add a normalization and go to the MLP and another normalization. And finally, the output of this goes into the linear layer, one linear layer, and then softmax, and then probability vector. We get the probability vector. Okay, so This is the overview of transformer. 자, 이거 그림 그냥 따라서 보면은 뭐 이야기 어렵지 않았을 겁니다. 그래서 간단하게만 얘기하면은 스킬 커넥션을 쓴다. 멀티헤드 어텐션을 쓴다. 마스크드 멀티헤드 어텐션을 쓰는 이유는 디코더 사이드에서 미래의 토큰을 보지 못하게 하기 위해서 쓴다. 미래의 토큰을 가린다. 그런 거죠. 그 외에는 그냥 그림을 차근차근 보면은 어렵지 않게 이해할 수 있을 겁니다. Okay, now the the auditive attention. So in the last lecture, we have studied the banana attention, which is additive attention, and this formulation is actually GPU memory inefficient. So this is the previous decoder hidden state. And this is the current hidden state, encoder side hidden state. Not current and previous. I minus 1. Sorry for the bad handwriting. Okay. Hmm. So Si minus 1 and Hj is has the d dimensions. And if we use the batch dimension, then we so we want to compute this attention in the parallel way, then we have to use multiple inputs, and then this will be matrix or tensor, right? So I use the capital character to indicate the matrix. Now this is n by d. N is the number of n is the batch size. D is the hidden size. Okay. Now we want to further parallelize this by removing the index. So now S and H is now they have different signs. So S is n by t by t. T is the upper sequence length. H is n by L by D. L is the input sequence length. Notice that this S and H has a different size, but we have to add them. So we process this S and H to make the same size, like M by T by L by D. This can be realized by using the unsqueeze in the torch language. Unsqueeze. And then repeat. So we already have seen the similar process in the last lab session. Okay. And here, this is very large number, too large, inefficient in terms of memory. Okay, so this is the limitation of banal attention. Okay, so far we have seen why this additive attention is inefficient in terms of GPU memory. On the other hand, the multiplicative attention. Multiplicative attention has been proposed. This is a long attention, which was covered in the last session, right? So let's see. This comes from the this figure comes from the original paper. So the notation is different. And if we use the same notation in the previous slide, then this is the Si minus 1, and this is the Hj. Not J. This is actually, because this is the all output from the all time step. So this is basically not single step output. This is H. So H is B by L by D. Not B, N. And WA is D by D. and uh, this is now as if we want to parallelize this, then and by because this from the decoder, this from the encoder, so and by t. Hmm. So we want to compute this, then uh, S transpose is we want to omit the batch size, batch dimension. So this is m by d by t. No, we do not need to transpose this. S and WA is n by t by t. And SWA H mhm. No. So this is very confusing actually. Hmm. Oh, it's weird. Wait a minute. Hmm. Okay, okay. So if we want to compute S and W first, then this will be n by t by d, right? And then we uh, we have to transpose H because this is basically the inner product. So this will be M by T by L. As we have seen in the lab section. Okay. And this is much more efficient in terms of memory. So this multiplicative attention is very important because this is used for transformer. Not exactly this form, but the motivation of this multiplicative attention is used for transformer. Okay, let's go to the transformer attention. So this transformer is very similar to room attention and with a scaling factor. And instead of one-sided linear transformation, the transformer attention transforms both sides. And this does not require additional cost if we parallelize it. So Q is S, W, S, H, W, H. Okay. So KQ transpose is H, WH, WS, no, S, WS transpose. This is equal to H, WH, WS transpose, S transpose. Okay. I will see the room attention again. And wait a minute. And this W, W and W are weights or parameters. H from decoder. No, encoder. S from decoder. And as you know, this can be treated as 1W, right? There is no non-linear activation layer here. So this is basically room attention. I see the room attention again. Sorry for the confusion. Actually, this is very, very confusing thing. So the conclusion remains the same. Room attention is much more efficient in terms of memory. And this is the inner product between HT and WAHS bar, right? And WAHS bar, if we use tensor H, this is H, this is the S, right? I want to use this S and H to make to reduce the confusion between this additive attention and multiplicative attention. And this WHS per can be formulated as HWA. Right? This is the column vector. And this is the, so this is, okay. We treat this as the column vector of the H, matrix H. And we do not care the transpose of WA because this is a learnable parameters, okay? So this, if we treat this as column vector, then this will be 1 by D. And here, this is the L by D, right? Okay. So this is H, and this is W, and this vector is we take inner product between this row vector and the column vector, right? That is, this is the 1 by D vector. So we can say this can be formulated as HWA. And the size is, so this is LD, DD, so L by D, N by L by D. And as we want to multiplicate, we want to take matrix multiplication between this HWA and S. Similarly, this can be formulated as S, but the size does not match. We have to transpose S because S is n by t by d. So for simplicity, we omit the batch dimension. So this is the d by t. This is the L by D. So we can multiplicate these two tensors and then it will be L by T. Finally, this will be R N by L by T. And this HWS transpose are exactly the room attention. But there is difference. There is a difference in terms of implementation. This H and S are linearly transformed by different uh, different linear transformation matrix. So the results are also can be different, but I heard that the result are almost the same. Anyway, I want to say in transformers attention, both sides are transformed. And then scaled. So if the hidden size is big, multiplying Q and K transpose will be big, which makes the attention spiky. What does this mean? So if your output, so attention takes softmax. For example, softmax what are the results of these two softmax? It will be 0.2 and 0.8, I think. And this will be 0 and 1. This is more spiky. So the scale of input of softmax matters. Okay. And we do not want to make the attention spiky. So we want to normalize this tensor, this object. How? By dividing the square root of d of k. That means it can be properly scaled by dividing by the square root of the hidden size. If q and k are random variables of mean 0 and variance 1, it can be proved that this division conserves the same mean and variance. Anyway, QK transpose. So there is no weight here because Q and K include the weight. Anyway, this is scaled. So this is the scale part. And then mask is optional, and nowadays we do not use mask here. So this is optional. And then take softmax. And then we take matrix multiplication with this output and V. Okay. So this is the attention QKV. Mm. And here is the multi-head attention. Single attention can only focus on one part of the sequence, right? So even if we take scale, this limitation is not fully reserved, but uh, this can be reserved further by using the multi-head attention. So what if we want the motor to focus on multiple parts of the sequence? Multi-head attention. So we use multiple number of attention. And this enables us to model a complex relationship with relatively few layers. So here is the H, it's the number of heads. Each head looks at different tokens. Okay, so that is how we can attention multiple tokens. Okay, so here, the attention, the each head is QKV, and here is the W. What is this? We want to make sure that each Q and K and V has different weight. So that is why there is the index I. And what is this QKV? This is just a notation. So this W is for Q, this W is for K, this W is for V. So V, Q, and V and K and Q are linearly transformed. And then scaled dot product attention. And then concatenate the head 1 to head H. And then linear, linear transform by WO. This is the multi-head QKV. So what about size? Uh, so this is the size of attention. What is the size of attention? Um, this is the N by T by L because N by L by T. Okay. All right. Uh, Actually, in practice, T equal L because this is self-attention. No. So there is no point for n by t by l or n by l by t. But anyway, k is from the encoder. So this is t by h is t by d, s is t by, no, h, no, no, l by t. And this is t by d. So kq transpose is l by t. So k n by l by t, n by l by t. And the softmax does not change. Oh, it's weird, I think. Oh, H, S is decoder, right? Hmm. And R is the source sequence length, and T is the target sequence length. So this is the L by T, and this is T by D. Hmm. Ah, I almost forgot V. V is HWV. Hmm. So KQ transpose should L by T, and V is L by D. So softmax KQ transpose over dk v should be n by l by t. Oops. It does not match. The size does not match here, right? Hmm. I I I must make a mistake here. I'm not sure what is the mistake because I think this is correct. Haha. Ah, okay. What is this? QK transpose. What is these things? QK transpose. Then the first computation was correct. Okay, so I'm sorry for the confusion. I'm sorry for any inconvenience. Uh, okay. Anyway, this is SWH, and the sizes are um, this is L, this is T. No, this is T, this is L. So T by L. So this is N by T by L. And this is the L by T, L by D. So finally, this attention, the size of the attention is n by t by t. Then head is t by d, head 2 also t by d, head h is t by d, so then this is t by hd, right? So this is very large tensor. So there are two approaches to make this correct. One method is we use the linear layer. So hd2t. We can make such as torch dot nn dot layer linear hdd blah blah. Okay, so this is the first approach. And the second approach is we use this weight w to d to the h d over h. Then this will be d to the I don't know d by no t by d t by h 분 h no d over h t over h t multiplied d over h. Okay, then if we concatenate then it will be t by d. Okay, so this is the second approach. 자, 첫 번째는 W5를 활용해서 HD를 D로 줄이는 방법이 있고요. 두 번째는 여기 있는 이 리니어 레이어의 폭을 조정해가지고 H분의 D로 우리가 변환을 시키고 마지막에 컨케이트넷을 하면 결과적으로 또 T by D가 나오겠죠. 제가 지금 T하고 L을 계속 구분하고 쓰고 있긴 하지만 사실 트랜스포머에서 T하고 L은 같아요. 그래서 이게 사실 그 무의미한 분리긴 한데 조금이라도 예전 프리비우스 노테이션과 일치시키기 위해서 지금 이렇게 하고 있습니다. Okay. In the next lecture, I will reformulate this multiplicative attention. So please stay tuned and see you in the next lecture.